Hello, myself Sherin. This video is part of the video series Architecting Machine Learning Systems. Machine learning revolves around making predictions and decisions based on data. But what happens when your data is unbalanced or you need your model to generalize well to new unseen data? This is where data sampling comes into play. In many real-world applications, you will encounter imbalanced datasets. In 2016, Microsoft's chatbot started making offensive and racist tweets after being trained on data from Twitter. The data it learned from was not properly filtered for harmful content. In 2018, Amazon had to scrap an AI recruiting tool that showed bias against women. The system was trained on past hiring data that reflected male-dominated technical workforce at Amazon, which caused this bias. In 2020, Stanford researchers found racial bias in an algorithm used by US hospitals to prioritize care. The algorithm was trained more on data from white patients. So these kinds of events happens all the time because of the data used for training was not carefully sampled. Consider the scenario of developing a fraud detection system for a credit card company. In this example, you are faced with imbalanced data where the vast majority of credit card transactions are legitimate or non-fraudulent, and only a very small fraction are fraudulent. Without addressing this data imbalance, a machine learning model may perform poorly at identifying fraudulent transactions because the number of fraudulent transactions used for training is considerably lower than the legitimate ones. It might simply predict that every transaction is legitimate, achieving high accuracy, but failing to detect fraud. To tackle this, data sampling techniques can be applied. You can oversample the minority class or undersample the majority class to create a more balanced data set. This way, the model gets exposed to a sufficient number of examples from the minority class, improving its ability to recognize fraudulent patterns and distinguish between legitimate and fraudulent transactions. Another key reason for data sampling is to prevent overfitting. Overfitting occurs when your model becomes too specialized in the training data, making it perform poorly on new unseen data. Data sampling allows your model to generalize better by exposing it to a diverse range of examples. Imagine you are developing a machine learning model to predict housing prices in a rapidly growing city. You have a data set that includes information such as the size of the house, number of bedrooms, distance to public transportation, and neighborhood crime rates. Now, without a proper data sampling, you might run into the problem of overfitting. Let's say the majority of your training data consists of houses built before the city's recent development boom, and you have a very few examples of newer or modern houses. Your model, if not properly regularized, might overfit to the historical data and fail to generalize well to new modern houses. To prevent overfitting in this scenario, you can use data sampling. You could collect a more diverse data set by deliberately sampling a larger number of examples of newer houses and ensuring a balanced representation of different types of properties. This diverse data set will help your model learn patterns that apply to a wider range of housing types, allowing it to make more accurate predictions on both older and newer properties in the city. Data sampling in this case ensures that your model doesn't become too specialized in one type of data, thus preventing overfitting and improving its ability to make accurate predictions on new unseen housing data. In a typical machine learning workflow, data goes through several stages, each of which plays a crucial role in the development and deployment of machine learning models. These stages can be summarized as data collection, data pre-processing, data sampling, data splitting, and feature selection or feature engineering stages. In data collection stage, we gather data from various sources. Then we clean, transform, and organize the collected data to make it suitable for machine learning in the data pre-processing stage. The next stage is data sampling, where we select a subset of data points from the collected data set. Data splitting refers to dividing the pre-processed and sampled data into training, validation, and testing data sets for model development and evaluation. In the feature selection or engineering stage, we choose relevant features and engineer new ones to represent the problem domain. Machine learning algorithms often require a large amount of data to train effectively. Processing all available data can be computationally expensive, so sampling reduces this burden. Storing and processing large data sets can be costly in terms of memory and computing power. Sampling mitigates these resource requirements, making the machine learning more accessible. Then, when developing machine learning models, especially during research and prototyping phases, working with smaller samples accelerates model training, testing, validation, leading to faster iterations. Sampling is often the first step in data analysis. It provides an initial understanding of data characteristics, distribution, and potential patterns, guiding future engineering and model selection. Data splitting for testing and validation is fundamental in building machine learning models. Sampling helps create training and test sets and is used in techniques like cross-validation or assessing model generalization. In scenarios where full data access is restricted due to privacy concerns, sampling allows you to work with a smaller subset while minimizing exposure to sensitive information, which is crucial in healthcare, finance, and other regulated domains. In real-time applications and edge computing, where resources are limited, data sampling is essential for processing efficiency, ensuring that machine learning models can run on devices with constrained resources. Sampling can be used to detect missing values and outliers in the data, which can impact model training and prediction accuracy. Sampling helps identify data quality problems early in the process. When working with limited data, the risk of overfitting increases. Careful sampling combined with techniques like regularization helps mitigate overfitting by providing a more generalizable data set. Sampling allows machine learning practitioners to start model development when collecting the entire data set may not be feasible or practical, particularly valuable in projects with limited initial data. In real-time or resource-constrained applications like IoT devices or edge computing, where processing power and memory are limited, sampling helps to make efficient use of available resources. During the initial stages of a project, when data may not be fully available or collecting the entire data set is time-consuming, sampling can expedite prototyping and testing. By working with a subset of data, you can assess its quality, detect missing values, and identify outliers, guiding data cleaning and pre-processing efforts. Properly conducted data sampling can lead to more accurate models, reduced biases, and a deeper understanding of the underlying data distribution. Simple random sampling provides an unbiased way to create a representative subset from a larger population of data. It works by selecting data points completely at random, giving every data point an equal chance of being chosen. To To illustrate its practical application, consider a scenario in a manufacturing plant where the quality control team needs to assess the quality of products produced in a day. They can employ simple random sampling by randomly selecting a set of items from the production line for inspection. The critical aspect here is that each item on the line has an equal chance of being selected. This approach ensures an effective means of identifying defects or quality issues in the production process. Systematic sampling is a method used to extract data points from a larger data set in a structured manner by selecting them at regular intervals. This technique proves valuable when you see a sample that accurately represents the entire data set while also simplifying the sampling process for practical reasons. To illustrate, consider a scenario where the city's transportation department aims to monitor the traffic flow at an intersection. Rather than meticulously recording data for every single vehicle that passes through, the department may choose to systematically count the number of vehicles passing at consistent time intervals, such as every 5 minutes. By doing this, they obtain a representative snapshot of traffic patterns throughout the day, making it easier to analyze and draw conclusions from the collected data. Stratified random sampling is a method used to gather data from a population in a way that ensures it accurately represents different subgroups within that population. To do this, the population is divided into distinct groups known as strata based on specific characteristics or attributes. For instance, consider a marketing company that aims to conduct a survey on consumer preferences. To ensure the survey reflects a diverse range of consumers, they might divide the population in the age categories 18 to 25, 26 to 40, 41 to 60, and so on. Then from each of these age groups, they randomly select participants to take part in the survey. This approach guarantees that the survey will include opinions and feedback from various age range, providing a more accurate representation of the entire consumer population. Cluster sampling efficiently creates representative samples when data points have an inherent grouping, like geographic regions or time periods, rather than sampling individual data points. All clusters are randomly selected. For instance, to study traffic patterns across a city, individual intersections could be prohibitively numerous to monitor. Instead, the city can be divided into regions, and a random sample of the region can be chosen. Traffic data is then collected from all intersections in the sample region, giving a manageable yet representative data set. Another example is testing product quality by batch rather than individual units. Cluster sampling provides an efficient way to create representative samples from naturally grouped data. It balances sampling practically with randomness to avoid systematic biases. The trade-off is precision, since looking at whole clusters gives less granular insights. A proper cluster selection is key to quality results. Imbalanced datasets are a common challenge in machine learning, where examples from one class significantly outnumber another. This skews models towards the majority class. Data balancing techniques help create a more proportional class distribution. Undersampling reduces examples from the majority class randomly. This ensures models have adequate minority class data, but can lose useful majority class information. Oversampling increases minority class example by duplication or synthetic data generation. This retains all majority data, but may overfit models on duplicated minority data. SMOT, which is the short form for synthetic minority oversampling technique, provides a balanced approach. it generates new synthetic minority data points by interpolating between real examples. This better retains minority information while avoiding overfitting from duplication. For instance, in fraud detection, non-fraud transactions dominate biasing models. Undersampling may lose useful non-fraud patterns, or sampling by duplication or fits on real fraud data. SMOT synthesizes diverse new fraud-like examples, balancing the classes better. The choice depends on the dataset properties and project goals. Undersampling is fast but risks information loss. Oversampling retains information but may overfit. SMOT provides a balance, improving diversity with the synthesized data. Together, these techniques enables handling complex class imbalance issues. Adaptive sampling dynamically adjusts the sampling strategy based on changes in the data or model performance. For instance, in fraud detection, if a new type of fraud pattern emerges, adaptive sampling can allocate more samples related to that pattern, improving detection. Important sampling focus sampling on critical events that are costly to observe, like natural disasters or rare defects. By oversampling important events, it improves risk analysis and quality control. Markov chain Monte Carlo, MCMC, is a computational technique used in machine learning and statistics for sampling from complex probability distributions. It's especially valuable when dealing with high dimensional or intractable distributions. MCMC generates a sequence of samples that approximate the desired distribution. Bootstrapping is a resampling method used in machine learning to create multiple datasets by repeatedly sampling data points from original dataset, often with replacement. Each new dataset can be used to train and evaluate models. In bootstrapping, you repeatedly and randomly sample the data with replacement to create multiple datasets called bootstrap samples. Each sample may contain some duplicate data points. You train and test your model on these bootstrap samples to estimate the model's variance. For example, companies conducting customer satisfaction surveys can use bootstrapping to generate multiple survey datasets by resampling responses from the original survey. This helps assess the robustness of the survey results and provide insights into the range of possible outcomes. Cross-validation helps assess how well machine learning models generalize to new data. It's critical when building models with limited training data, which is a common challenge. The available data is split into distinct subsets called faults. The model is then trained on some faults and tested on the remaining fault. This is repeated across different combinations of test and train faults. For example, in 5-fault cross-validation, the data is split into 5 faults. The model is trained on 4 faults and tested on the remaining fault. This is repeated 5 times using a different fault for testing each time. The performance across test faults is averaged to estimate the model's overall ability to make accurate predictions on new data. If performance varies significantly, it indicates that overfitting that needs to be addressed. A cross-validation maximizes the use of limited data by testing the model on different subsets. It simulates how the model will generalize to unseen real-world data. Techniques like regularization can reduce overfitting exposed by cross-validation. Spatial sampling selects data points based on geographic distribution to represent an area. It is vital in applications like environmental monitoring, transportation planning, and emergency response. In many applications, it is useful to retrieve the most important or relevant items from a large data set. Top K sampling does this by selecting the top K data points based on assigned scores or values. It's often employed in various applications where ranking and prioritizing items are essential. For example, if search engine ranks web pages by relevance to a query, displaying the top 10 results ensures users to see the most useful pages first. The search engine uses top K sampling, where K is 10. Similarly, customer support softwares can prioritize tickets by severity. Top K sampling identifies the K most urgent tickets for agents to handle quickly. This provides better customer service for high priority issues. Recommendation systems also use top K sampling. The algorithm scores products or content based on users' preferences. The top K suggestions that align best with the user's interest are recommended. Reservoir sampling is a random sampling technique used to select a subset from items from a larger dataset when you don't know the total number of items in advance. It's particularly useful in scenarios where it's impractical to store or process the entire dataset, yet you need a representative sample. Imagine you want to conduct an online survey to collect feedback from your customers, but you don't know how many customers will respond. Instead of storing all responses, which might be resource intensive, you decide to use reservoir sampling. You create an empty reservoir to store customer responses. As customers start responding to your survey, the first K responses are placed directly in the reservoir. These are the initial n number of responses you collect. For each subsequent response, you generate a random number between 1 and the total number of responses received so far. If the random number fails between 1 and n, you replace the corresponding response in the reservoir with the new response. This process continues as more customers respond. With this approach, you end up with a random but representative sample of n customer responses, regardless of how many responses you receive in total. It ensures that every customer's response has an equal chance of being included in the sample, making it useful for analyzing and making decisions based on a limited yet representative dataset. Quota sampling is a non-probability sampling technique used to gather sample of individuals from a population. Unlike random sampling methods, where each individual in the population has an equal chance of being selected, quota sampling involves dividing the population into subgroups or strata based on specific characteristics, and then selecting a predetermined number of individuals from each subgroup to form a sample. It's commonly used in situations where random sampling is difficult or impractical. Suppose you are conducting a political poll to gauge public opinion in a city. The entire population consists of various age groups, and you want to ensure your sample represents these age groups in a proportion to their prevalence in the city. Using quota sampling, you can achieve this without selecting individuals entirely at random. Stratified random walk sampling is the combination of two methods: stratified sampling and random walks to select a diverse set of data points from a data set. The goal is to ensure that the chosen data points represent various subgroups or strata within the dataset, while also introducing a touch of randomness through a random walk process. Imagine a healthcare study investigating the effectiveness of a new medical treatment. Researchers aim to gather a sample of patients that accurately reflects from different demographics such as age, gender, and medical history. The They maybe initially categorize the patient data into groups based on demographics, creating strata like different age groups, genders, and medical histories. Now they incorporate a random element into the sampling process. This means they randomly start from one patient within a stratum and moves to other patient based on certain rules, such as following connections between similar medical conditions or age groups. As the random walk progresses, it selects patients from different strata while occasionally introducing an element of unpredictability. This helps maintain a level of representation from each stratum in the final sample. Proper data sampling techniques are essential for machine learning systems when they transition into production. While the development of prototyping phases may involve more flexible and exploratory sampling methods, the transition to production requires a more rigorous and stable approach. Ensure that the data sampling process in the production environment is fully reproducible. The same data points should be used for training, testing, and validation every time to guarantee a consistent model performance. Use a cloud-based data lake or data warehouse that stores raw and processed data from various sources. For example, Amazon S3, Google Cloud Storage, Snowflake, or BigQuery. For data ingestion, use services which provides features to extract, transform, and load data from the data sources to the sampling environment. And we can use services like Apache, Airflow, AWS Glue, Google Cloud Dataflow, Stitch, etc. for this purpose. Use the frameworks or libraries that implements various sampling techniques and algorithms to select a subset of data for model training and testing. For example, scikit-learn, TensorFlow data, PyTorch data loaders, Spark mlib, etc. The production data set, even if sampled, must be representative of the real-world data distribution. Biased or under-representative samples can lead to suboptimal model performance when exposed to diverse data in the production environment. The sampling method should remain stable over time. Data changes and shift in data characteristics can affect model performance. Regularly assess whether the initial sampling technique still aligns with the evolving data. For example, a recommendation system for an e-commerce platform regularly updates its product catalog. The sampling method used for training the recommendation models need to remain stable and relevant as new products are added and with the changes in the trend. Implement automation for the sampling process in the production pipeline. Depending on your infrastructure, you may need to regularly update your dataset, retrain models, and make predictions. Automated sampling ensures consistency. For example, a fraud detection system for a financial institution. Automated sampling ensures that the model continuously trains on the most recent data to detect new types of fraudulent transactions as they emerge, maintaining the system's effectiveness. Consider the scalability of the sampling method. As the data volume grows, you should still be able to sample efficiently and maintain acceptable processing times. Establish a strategy for when and how often you refresh your production data set. Depending on the problem, you may need daily, weekly, or monthly updates. Plan for the acquisition and integration of new data. Implement monitoring of model performance in production and set up a feedback loop. If model performance degrades over time, it could be due to changes in the data distribution. Revisit your sampling techniques when necessary. For example, an email filtering system monitors the performance of its spam detection model. If there is a sudden increase in false positives, it triggers a review of the sampling techniques to identify potential changes in the spam email patterns. Always prioritize quality over quantity when it comes to data collection. Having more data is not always better if that data is poor quality or not representatives of the population you are interested in. Continuously monitor for biases in your data, especially if your sampling technique is subject to biases. Implement strategies to mitigate these biases to ensure fair and ethical decision-making by the model. If you are sampling sensitive or confidential data, follow the best practices for data privacy and security. Anonymize or encrypt data as necessary to protect privacy. Implement a thorough logging and auditing mechanisms for your data sampling process. This is essential for traceability, debugging, and compliance with data governance regulations. Ensure that your data sampling and usage align with legal and ethical guidelines, especially in industries with stringent regulatory requirements. Maintain backups of your sampled data sets and use version control. This allows you to revert to a previous data set if issues arise. Use AWS backup, Google Cloud Storage, Azure backup, etc. as it fit for your requirements. And to version sample datasets, use DVC, Pachyderm, Delta Lake, or JIT. Document your sampling methodology, parameters, and reasons for selecting specific techniques. This documentation is vital for transparency, audits, and knowledge sharing among team members. Have plans in place for disaster recovery, including data loss and corruption. Redundancy measures for data storage and processing pipelines can ensure system robustness. Okay. Today, we have discussed different stages in machine learning data workflow, the role of data sampling in building effective machine learning systems, different sampling techniques, best practices, and related technologies. That's it for now. Please subscribe if you haven't done already to receive new video alerts. Stay tuned. Bye for now. Thank you.